Welcome to my talk on the Riemann hypothesis, and I want to talk about the Polya density, or the Riemann Polya density approach to showing the Riemann hypothesis, and I want to provide a couple of new insights. Okay, so just very very quickly, what's the Riemann hypothesis, or Hilbert's H problem? So Riemann back in 1859 talked about the zeta function and the psi function. So the zeta function is just defined as that well-known sum, and outside the region real s bigger than 1, you have to have some form of analytical continuation to make sense of that sum. And the xi function is essentially a regularized version of the zeta function, and essentially all non-trivial zeros of the zeta function correspond to the psi function, so we can spend our time looking at the xi function rather than the zeta function. And the famous Riemann hypothesis states that all non-trivial zeros of the zeta function, so equivalently a psi function, lie on the critical line real s equals a half. Or equivalently, those of the xi function evaluated at a half plus is, and by symmetry that's equal to xi over half minus is, equivalent that that function lies on the real axis. Okay, so the Polya approach was to essentially write the xi function as a Fourier transform, and then to look at properties of the real zeros of Fourier transforms. So we'll talk about that. Another important fact to note is something called the Euler product formula. So the sum can actually be written as a product over prime. It's really quite a remarkable result. That the sum as n goes from 1 to infinity of n to the minus s is the product over primes of 1 minus p to the minus s to the minus 1. And essentially it was Riemann that proved the symmetry or reflection formula for the psi function. And then one other little fact, that the Euler product formula only works for real s bigger than 1, so some form of analytical continuation is used, and in previous videos I like to use Ramanujan's master theorem to do that. Okay, so a quick little review of what's known about the Riemann hypothesis. So another way of saying it is that if xi of s is equal to 0, then that must mean that the real part of s is equal to a half. A very famous book by Tishmarsh on the theory of the Riemann zeta function. We know that it has a Hadamard product, and we know it's an entire function of order 1. And Riemann, in his classical paper, showed that 2xi of s is equal to a Mellin transform of a random variable y. And we actually know a little bit about the random variable y. It's essentially the moment generating function of y squared. Is actually a pretty simple, nice known function. But of course, we want to put this into Laplace transform space. So in fact, the random variable that we're interested in is actually the logarithm of y. And that's sort of where the difficulty comes in. Okay. So what was Polya's approach to the Riemann hypothesis, essentially in the 1920s? So Polya started a research paradigm that talks about finding zeros of, or real zeros of Fourier transforms. So give me a Fourier transform f of s with some underlying density phi of t. What properties of phi ensure that this only has real zeros. And so that's Polya's approach to the Riemann hypothesis. And so I'm going to call phi the Riemann Polya density. So we're going to talk about properties of phi. Now, in a couple of other videos, I talk more about my approach to the Riemann hypothesis, that rather than dealing with Polya's approach of looking at property densities, we'll actually look at the reciprocal psi function and look at something called Thoron's condition, and essentially the Riemann hypothesis is equivalent to finding a Thoron measure of something called a generalized gamma convolution. Okay, so this talk is about the Polya density and finding zeros of Fourier transforms. Now, there's a class of probability distributions, infinitely divisible ones, De Finetti, Levy, and Kolmogorov, the late 1920s and early 1930s, talked about these types of random variables, and Khinchin basically proved that as long as sigma is bigger than 1, so essentially you can just use the Euler product form, that essentially the psi function can be written as a Fourier transform of an infinitely divisible random variable, and we know that by properties of infinitely divisible random variables that they don't have any zeros. Okay. Now, what makes the Riemann hypothesis hard is that when we go to the into the critical strip, so when we go from a half to 1, remember that the psi function is symmetric, so we don't have to bother to go from 0 to a half. When we go into that strip, it turns out that the ratio, or the psi function here, normalized, is actually not infinitely divisible. But it's actually quite close to infinitely divisible, and essentially the Levy measure is what's known as a signed measure because of the cosine term. Sometimes people call that pretend infinitely divisible. So not quite infinitely divisible, but there's a Levy-looking formula for it. Okay, so that's what makes it a lot harder than the case sigma bigger than 1. Now, in a recent YouTube video, I talked about a dual approach. So rather than just taking this Riemann Polya approach, remember that essentially looks directly at the psi function, writes it as a Fourier transform, and looks at properties of real zeros of Fourier transforms. There's an equivalent theory that looks at the ratio function, essentially Bonnesen and Thorin, or Thorin's condition, and something called a generalized gamma convolution. And this little condition here is related to what's known as a Van Danzig pair or walled couple. And so there's an equivalence of the Riemann hypothesis is essentially to check this thing called Thorin's condition. As I said, my previous videos have looked at that. Or as Leonard Bonnesen would say, that the ratio function is a hyperbolically completely monotone function. And again, why is that very useful? Although we won't discuss it more here, it's very useful because we know that that the Laplace transform of a GGC is analytic on the cut plane, cut complex plane. So even though we check this condition only for real S, we know that right-hand side can't be infinite. So we know that this thing here can't have any zeros. So x psi of a half plus root S is not equal to 0 for real S bigger than 0. And from that, we can essentially prove the Riemann hypothesis. Okay, so today's talk, we're going to look directly at the Riemann Polya approach and propose a couple of new thoughts there as well. Okay, so let me be explicit. What exactly is the Riemann Polya density? So, Riemann basically found the density in terms of Jacobi functions. So theta is a Jacobi function. We'll define a function h, so you can see that h will be related to the density underlying the Laplace transform or moment-generating function that defines a psi function. H is defined essentially by an integration by parts, essentially as a derivative of y squared g prime. So this is actually a density, it's positive. We'll see in a second that the density from properties of Jacobi functions and H is actually symmetric. And you can see that looking in density space is actually quite hard, right? It's a complicated looking density. This term here looks like something like a Gumbel or extreme value distribution. And actually, given symmetry, we can actually replace x by absolute value of x. And essentially, we can look at something called a half Gumbel distribution, which you'll see later. But again, it's weighted, and it's a big mixture distribution. So you can see tackling the problem of looking directly up here, if I replaced S by AS, directly looking up here at the Fourier transform of this Riemann Polya density and checking to see whether checking the zeros properties can actually be quite difficult. As opposed to, let me just recap down here, as opposed to Thorin's condition, where I can directly find the Levy measure representation for the ratio function, and then find from the Levy representation a Thorin measure and prove it as GGC. So essentially there are two different approaches to to showing the Riemann hypothesis. Okay, so let's spend a bit more time and see if we can make headway in the Riemann Polya paradigm. So what do we need to know here? So just a quick little summary. That H function that we defined on the last page essentially defines the Mellin transform. So this was essentially Riemann all the way back in 1859 in his classic paper. We'd like to evaluate it at sigma. We'd also like to evaluate in the case when sigma is equal to a half. And essentially we can find that symmetric density that we talked about on the other page. And it's symmetric because of, if I look at the condition, the properties of the H function from the Jacobi function, we have this identity here. So essentially, Riemann and Polya found the density that provides the Fourier transform of the psi function. Okay, so let's take that Riemann-Polya representation in terms of the Fourier transform. Because it's even, we can write an integral from 0 to infinity. And under Riemann hypothesis, essentially what we're asking is, can we find a factorization of xi over half plus is in terms of a Hadamard product that looks something like this? So the zeros are essentially given by plus or minus rho. So does it have any real zeros? And so Polya's framework is to take the Fourier representation of this and just to directly ask that question in terms of what are necessary and sufficient conditions on an even probability density for its characteristic function of Fourier transform to only have real zeros. Okay, so here's an interesting class of functions. If you look at entire functions of order 1, there's the Hadamard product. The important special case which would apply to our psi function is if it's even with zeros plus or minus rho, then essentially we can write the ratio function as the product of rho squared over rho squared plus s squared. And as I said, this will lead to a GGC representation. How does one do that? So let's start with the ratio. Write it as an exponential integral with respect to a Thorin measure, which is a sum of Dirac measures sitting at those zeros. There's a duality between Thorin measures and Levy. So up here is Thorin. Here is Levy, Kolmogorov. And essentially the duality comes from the Levy measure being a completely monotone function, and us using Frulinelli's identity, which is sort of a key identity in this theory of GGC random variables. So an equivalent approach to the Riemann hypothesis that I've talked about in previous videos is you can show that the ratio function is essentially a Laplace transform of a GGC. Okay, let us go back, and so there's one of two ways of going, right? Either you take the Riemann-Polya approach, look at the characteristic function, and try and show that you can directly factorize the characteristic function as a product that looks something like this, 1 minus s squared over the 0 squared, or you can take that ratio function, essentially show it's equal to a Fourier transform of what's known as an EGGC, or symmetric EGGC, which in turn will be equal to a Laplace transform with respect to a GGC. How does one get there? Well, essentially L is a Laplace distribution. Why do I get that? Well, the Fourier transform of a Laplace is simply 1 upon 1 plus s squared. So essentially you can see how that can come up here. And essentially I'm going to have a sum over scaled Laplaces to get this function that looks like this. So the Laplace with density e to the minus 1/2 absolute value of x is known as a extended generalized gamma convolution. It's essentially a scale mixture of normals where the mixing measure, if I'm explicit, where the mixing measure is given by h. Which another way of saying that is that the Laplace is a difference of exponentials and the GGC is a convolution of exponentials with means that those zeros rho sub n. And again, so, there's two paradigms. The Riemann-Polya paradigm is this one. The Bonderson-Thorin paradigm is this one. Now, so let's go and look again a little bit more at the Riemann-Polya one. It's hard to characterize the class of functions that can be factorized this way. So let's see if we can make some progress there. And there's a very nice paper by Polya. Mark Kack as well has a very nice discussion of these Polya papers in the 1920s. And so Polya directly addressed the question, what properties of the function f are sufficient to assure that the integral only has real zeros? And there's precisely one of his motivations, looking at the Riemann psi function, and again a whole class of functions down here, including Bessel functions, etc. And another nice paper that looks at classes of these functions is De Bruijn. Again, I think with a similar title, on the roots of certain trigonometric integrals. De Bruijn has a paper in the 1950s that also looks at these types of functions. Okay, so we'd love to be able to directly apply Polya's theorem directly to the density that is in the Riemann-Polya approach. Okay, well, how would we do this? Well, so Polya came up with a very clever, cute little theorem. Also, Titmarsh, I think section 10.24 of Titmarsh also has a similar theorem. So suppose that G is essentially an entire function of order 1. For real Z takes real values and has only real zeros and must have at least one zero. Then the clever little trick is that you can start to look at essentially mixtures of these functions. So essentially the function G evaluated as Z plus IA plus G evaluated as Z minus IA also only has real zeros. Okay, so how would you prove that? Essentially you prove by contradiction. So you start with it's an entire function of order 1, so you have a nice Hadamard factorization with only real zeros, so you know that these alpha n are the non-zero real zeros of G, right? And then you just say, okay, suppose I have a zero of that composite function or that additive sum, that mixture, and essentially you want to argue by contradiction. You just want to show that y must equal to 0, so it must have real zeros. And again, as I said, Mark Kack has a very nice discussion of for like spin systems, and essentially that became the basis of Li-Yang theory. And Neumann also has a nice discussion of this, something called ferromagnetic random variables. And it's a very clever, cute little proof. So if I just go up to my Hadamard Weierstrass factorization, and if I take this equal to 0, I know that the two moduluses must be the same. Take the ratio, so I know that the ratio of moduluses must be 1, and I can actually put that in Hadamard Weierstrass form. And you see that in the two cases, if y is bigger than 0, or if y is less than 0, then essentially you get a contradiction. The ratio can't be equal to 1. So a simple argument by contradiction shows that y must be equal to 0. And a number of people have generalized this theorem further. There's an interesting set of papers by Cardon recently that looks at looking at much more complicated mixtures that come here, and that will be our approach as well. So it's a very clever little theorem due to Polya. I call it the Polya-Kack theorem. If you start off with a simple class of functions that only has real zeros, you can essentially do mixtures and combinations, and that set of Fourier transforms will also only have real zeros. And essentially this is how Polya tackled the Riemann hypothesis, or how to go at it. He started with the class of Bessel functions, which we know only have real zeros. As I said before, De Bruijn extends this class, and you see a lot of these number theory problems involve Cauchy integrals. For example, in De Bruijn's paper, he has a very nice discussion of the Ramanujan tau function and the density that corresponds to that. And again, it looks very similar to the Riemann-Polya density with lots of Cauchys in them. And Polya's approach was essentially to look at an approximation of the Riemann psi function. So it doesn't exactly equal it, but it's got similar tail properties and it's actually very close. And essentially he proves that if you take a sum of two Bessel functions, and again, there's our theorem, we look at the two Bessel functions evaluated at 9/4 plus a half IS, 9/4 minus a half IS. Essentially, we can just use Polya's theorem and show that what Polya called the falsified psi function has only real zeros. So that was his hope, that you could take the Riemann psi function and essentially approximate by a mixture of Bessels and essentially show that it only has real zeros. Okay. Now, how can we add to that? Well, there's a very cute little probabilistic fact by Christensen, a theorem of Stoutel, that shows that mixtures of gamma 2s are what's known as infinitely divisible. And remember, infinite divisibility is such that the Fourier transform will not equal to zero. So properties of infinitely divisible distributions, Levy and Khinchin used it to look at the Riemann or look at the psi function when sigma was bigger than 1. And actually, one of the rather interesting things is that the second you go to powers bigger than 2, it's like a boundary point. It's essentially not infinitely divisible. Now, how do we use mixtures of gamma 2s? Well, again, if we look at that Riemann Polya density, it essentially has half Gumbel terms in them. So here I'm looking at x bigger than 0. Again, I have to be a little bit careful with conditions on some of these coefficients to make sure that I still have densities. Remember, I want G to be a density. Well, if I look at a half Gumbel over here, essentially I can write a half Gumbel as a mixture of gamma 2s. And so there's the gamma 2 that's sitting in here, and lambda is random with a mixing measure G. So a very clever, cute little trick is I can take half Gumbels, write them as mixtures of gamma 2s, and essentially I'm going to try and apply the Polya's theorem to this class of functions. And again, why is that useful for my Riemann psi function? Why would it maybe provide a direct proof? Well, again, if I look at Riemann's original paper, so he starts with the Jacobi function at the top, and Riemann's classic formula for the psi functions given by this. Again, I can put it together with it using another identity, and I can essentially write the Riemann psi function in terms of a Fourier transform of a symmetric function that depends on the Jacobi function. And there's a cute little definition. Again, if we knew properties of Jacobi functions, remember that psi of x at the top is essentially given by the Jacobi function. We'd be able to prove that it's symmetric. So starting with Riemann's original classic identity for writing xi in terms of a Fourier transform of this big psi function, what do we have? Well, symmetry gives us these first two lines, and then there's a very cute little identity that people haven't seemed to realize. Essentially, the identity comes essentially from the normalizing constants of a normal distribution. I'm integrating over V, and essentially that identity is true. Why is that true, or why is that useful? Essentially, I can rewrite the Riemann Polya as a mixture, essentially, or of half Gumbels. And then remember, from the Christian result, I then want to write mixtures of half Gumbels as mixtures of gamma 2s. Okay, so the question is, can I rewrite this as mixtures of gamma 2? And can I then use the infinite divisibility? And then can I use that Polya trick, Polya's theorem, which writes things as mixtures of known entire functions that only have real zeros. And again, with all these things, the devil is in the details. There's a little bit of truncation, and you've got to check that densities are positive. But I think that's an interesting exact representation of the density that sits in the Riemann Polya theorem. So again, maybe there's hope in that regard. Just one more little observation. Another paper that seems to have passed people by is by Mataki in 1951, and he's got a very clever little trick for again rewriting exactly. So again, as opposed to the falsifies psi function of Polya, this provides an exact mixture representation, and essentially it's looking similar to like a mixture of Bessels. So again, I think that's another interesting approach. Okay, so let me finish with a discussion. So as I've said, there's a couple of approaches to Riemann hypothesis. One approach is this, just to take the density approach, essentially to look at f of s in our notation of Van Danzig pairs. Riemann and Polya both showed that the psi function can be written as a Fourier transform of an even function. The trouble is that density is rather nasty, and the observation here is can you rewrite that density in terms of a mixture of gamma 2 and then directly apply Polya's theorem. And then, of course, the second approach is to basically apply Van Danzig pairs and Wall couples and the theory of GGC random variables. Okay, thank you. Thank you very much for listening.